Welcome to section 2.3. We will use functions to describe real relationships, study several important families of models, find market equilibrium, and construct models from verbal conditions. The goal is not merely to manipulate formulas. We want to understand what each variable means, what inputs are reasonable, and what the model tells us about the situation. A model is a simplified mathematical description of a real situation. A complete model must define its variables, units, domain, and interpretation. Otherwise, the formula is just algebra wearing no identification badge. A model describes the main pattern rather than every observed value. Predictions inside the data range are usually safer. Predictions far outside that range ask the model to travel without a map. Substituting 4 gives 2,340 visits. Always attach the context and units to the result, because 2,340 by itself could be visits, dollars, or very enthusiastic pigeons. The slope is the monthly rate of change, while the vertical intercept is the initial predicted value. Interpreting the parameters turns the equation into information. Polynomial functions use non-negative integer exponents. Their formulas involve no variable in a denominator and no fractional or negative powers, so every real input is allowed. The first and fourth functions are polynomials. Negative and fractional exponents disqualify the second and third functions from the polynomial family. Mathematics has standards, apparently. A linear function changes at a constant rate. The slope measures output change per unit of input, and the intercept gives the output when the input is 0. Use the two cost and time points to calculate the slope. The result, $8 per hour, is the variable part of the rental cost. Substituting one known point gives the intercept. The completed model separates the $15 initial fee from the $8 hourly charge. The graph of a quadratic is a parabola. The sign of the leading coefficient determines its opening, and the vertex locates its maximum or minimum. Evaluating the quadratic at 40 predicts revenue of $6,400. The input is restricted to the realistic ticket range from 0 to 120. The vertex occurs at 60 tickets and gives the maximum revenue of $7,200. The graph confirms that revenue rises, peaks, and then falls. A rational function is a quotient of polynomials and cannot accept zeros of its denominator. A power function has one real exponent, and that exponent controls its domain and shape. At 40 participants, The average cost is $138. At 120 participants, it falls to $58 because the fixed cost is shared among more people. Algebra excludes 0, but context is stricter. Attendance must be a positive whole number and may be limited by capacity. The formula opens the door. Reality checks the guest list. Demand and supply express price as a function of quantity. Demand usually slopes downward, while supply usually slopes upward. Their intersection identifies a balanced market. At equilibrium, the demand and supply curves give the same price for the same quantity. Solving one equation provides the quantity, and substitution provides the price. Equating demand and supply gives x equal to 24. Because x is measured in hundreds, the equilibrium quantity is 2,400 units. Substituting 24 into supply gives $42. The graph shows the same result as the intersection of the decreasing demand curve and increasing supply curve. The nonlinear equilibrium equation produces two algebraic roots. We must use the domain and meaning of quantity before deciding which root is acceptable. The negative root is algebraically correct but contextually impossible. Keeping x equal to 8 gives an equilibrium price of $52. Algebra proposes candidates. Context conducts the interviews. Model construction begins by defining variables and writing the target quantity. A condition then removes extra variables, and context determines the appropriate domain. The garden uses 2 widths and 1 fenced length, so the condition is 2x plus y equals 180. Solving for y prepares us to write area using only x. Substituting the fencing condition into area gives a quadratic function of x. Now negative dimensions restrict x to the interval from 0 to 90 meters. Revenue is the number of tickets multiplied by the price per ticket. Both quantities depend on x, so their product creates a quadratic revenue model. The price restriction gives x at most 200. Since x counts additional people, the domain contains whole numbers only. Half a passenger would create more problems than it solves. Cutting out squares of side x creates box height x. Each base dimension loses x from both ends, so the base becomes 30 minus 2x by 30 minus 2x. Multiplying the three dimensions gives the volume function. Positive height and base length restrict x to values strictly between 0 and 15 centimeters. Polynomial, linear, quadratic, rational, and power functions provide a versatile modeling toolkit. Regardless of the family, always compare the mathematical domain with the real-world restrictions. A good modeling solution defines variables, builds the function, performs the mathematics, and returns to the context. Domain checks are part of the solution, not optional decoration. The main lesson is that a formula becomes meaningful only when its variables, units, domain, and interpretation are clear. Wisdom of the day. All models simplify reality. The good ones simplify the right parts.